In mathematics, spectral graph theory is the study of properties of a graph in relationship to the characteristic polynomial, eigenvalues, and eigenvectors of matrices associated to the graph, such as its adjacency matrix or Laplacian matrix. An undirected graph has a symmetric adjacency matrix and therefore has real eigenvalues and a complete set of orthonormal eigenvectors. While the adjacency matrix depends on the vertex labeling, its spectrum is a graph invariant. Spectral graph theory is also concerned with graph parameters that are defined by multiplicities of eigenvalues of matrices associated to the graph, such as the Colin-de-Verdier number. Isospectral graphs. Two graphs are called isospectral or cospectral if the adjacency matrices of the graphs have equal multisets of eigenvalues. Isospectral graphs need not be isomorphic, but isomorphic graphs are always isospectral. The smallest pair of non-isomorphic cospectral undirected graphs is K1, 4, C4 UK1, comprising the 5-vertex star and the graph union of the 4-vertex cycle and the single-vertex graph, as reported by Kalatz and Sinogowitz in 1957. The smallest pair of non-isomorphic cospectral polyhedral graphs are any ahedra with 8 vertices each. Almost all trees are cospectral, i.e., the share of cospectral trees on n vertices tends to 1 as n grows. Isospectral graphs can also be constructed by means of the Sun-Arda method. Another important source of isospectral graphs are the point collinearity graphs and the line intersection graphs of point-line geometries. These graphs are always isospectral but are often non-isomorphic. Cheaver inequality. The famous Cheager's inequality from Riemannian geometry has a discrete analog involving the Laplacian matrix. This is perhaps the most important theorem in spectral graph theory and one of the most useful facts in algorithmic applications. It approximates the sparsest cut of a graph through the second eigenvalue of its Laplacian. Chigi constant. The Chigi constant of a graph is a numerical measure of whether or not a graph has a bottleneck. The Chigi constant as a measure of bottleneckedness is of great interest in many areas. For example, constructing well-connected networks of computers, card shuffling, and low-dimensional topology. More formally, the Chigi constant h of a graph G on n vertices is defined as where the minimum is over all non-empty sets S of at most n, 2 vertices, and as the edge boundary of S, i.e., the set of edges with exactly one endpoint in S. Cheaver inequality. When the graph G is d-regular, there is a relationship between H and the spectral gap d minus lambda 2 of G. An inequality due to Tanner and independently Alon and Millman states that this inequality is closely related to the Cheager bound for Markov chains, and can be seen as a discrete version of Cheager's inequality in Riemannian geometry. Historical outline. Spectral graph theory emerged in the 1950s and 1960s. Besides graph-theoretic research on the relationship between structural and spectral properties of graphs, another major source was research in quantum chemistry, but the connections between these two lines of work were not discovered until much later. The 1980 monograph Spectra of Graphs by Cvetkovic, Dube, and Sachs summarized nearly all research to date in the area. In 1988 it was updated by the survey Recent Results in the Theory of Graph Spectra. The third edition of Spectra of Graphs contains a summary of the further recent contributions to the subject. Discrete geometric analysis created and developed by Toshikazu Sun-Arda in the 2000s deals with spectral graph theory in terms of discrete Laplacians associated with weighted graphs, and finds application in various fields, including shape analysis.